Hi guys, so now we're going to solve more problems on the Laplace transform. Okay, so here we have find V naught of t in the circuit shown. So that's the voltage across the ohm resistor. Note that since the voltage input is multiplied by U of t, okay, that's this. Your voltage input here is 30 e to the negative 2t times U of t. So remember the unit step function has a value of 0 for t less than 0 and 1 for t greater than or equal to 0. So that means for t less than 0, this source has been very, very off. Okay, 0 voltage here means this is a short and that our inductor has been unable to charge. Meaning, essentially, all this is saying here is that your initial conditions are 0. So you have no initial conditions, which is essentially what's happening here. It really makes the solving a bit easier. That's how to analyze the circuits. The voltage source is a short for t less than 0, and the initial current across the inductor is 0. We've established that. So let's get to solving. We're going to transform this into the frequency domain equivalent. Okay, plus minus. Remember, since there are no initial conditions, then all the same elements present in time will be present in frequency. If you had initial conditions, then you need to, add a voltage source to account for that. Add a current source depending on how it is. Okay. Boom. Let's find the Laplace transform. So this is 30 e to the minus 2t. So the Laplace of 30 e to the negative 2t is the same as the Laplace of, you can bring 30 out, e to the minus 2t. That's 1 over s plus 2 times 30, big X. 30 over s plus 2. The Laplace of an inductor, okay, is going to be SL. So that's going to be S plus S times 2, which is 2S. So this is 2S. Okay? We're going to do I1. We're going to do a mesh analysis. I2. Erase, so I have space to work. Boop, ba, booba, doobra, doop, doop, doop. Doo doo. Let's get to work. Minus 30. Okay, let's start with I1. Okay, so minus I1 plus 2s into I1 minus I2. You're going to equal 30 over s plus 2. Let me see if I can factorize out. Why is this minus I1? It's plus I1, pardon me, okay? So that's I1 into 2s plus 1 minus 2s I2 is equal to 30 over s plus 2. So this is for loop 1. Alright, for loop 2, same concept. Alright, 2s is I2 minus I1 plus 2 I2 is going to equal 0. What do we do here? I2 come out, so s plus 2 is going to equal 2s I2. 2 I1. Oof, fishy mathematics. Yes, 2s I2. Okay, so divide both sides by 2. We're going to have I2 s plus 1 is equal to s I1. Making I1 subject to formula, I have I1 is equal to I2 s plus 1 all over s. Pretty neat. Throw this guy back into where you see I1 here. Okay, so it's going to be I1, that's I over 2s. Okay, so let's do it this way. S plus 1 multiplied by 2s plus 1. Okay, multiplied by I2 all divided by s. Alright, then for my first equation, minus 2s I2 is going to equal 30 all over s plus 2. Let's expand this bracket. 2s squared plus s plus 2s, so that's plus the s. 2s squared plus s plus the s plus 1 all over s I2 minus 2s I2 equal 30 over s plus 2. Really, really funny stuff. If you divide this by this, it's going to be 2s I2. So we can use this term lose this term. So we end up with 3s plus 1 all over s is going to be 30 over s plus 2. What do? Cross multiply, okay? 3s plus 1. Where's I1? Where's I2? Okay, yeah, it's outside here. I2. 3s plus 1, s plus 2. I2, you're going to equal 30s. What do? Make I2 subject of formula. I2 is do a line. Where's your line? Okay. So I2 is going to equal 30 all over 3s plus 1, s plus 2. But we're not looking for current 30s, pardon me. We're not looking for current. We are looking for voltage. And recall that from Ohm's law, V is IR. Okay, for Ohm's law, same as IZ, complex impedance. Okay, so our current is this and our Z is 2. So V naught as a function of S is going to be 2I2. These are functions of S because they're common. You've got S here. So that's the numerator is going to be 60. Okay. So V naught is going to be 60. Let's 60 over 60s. Then we have 3s plus 1, s plus 2. What do? Partial fractions. What do? Partial fractions. What do? Partial fractions. A over 3s plus 1, close the bracket, plus b all over s plus 2. Stupendous. Multiply both sides by the denominator of this. That's going to be 60s is equal to a into s plus 2 plus b into 3s plus 1. Pretty amazing stuff. Set s equals minus 2. Very mischievous. Okay? So when you set s equal to negative 2, you let this entire, the coefficient of a tend to 0. So you can sneakily find a way to solving only for b. Alright, so this times minus 2 is going to be minus 120. 3 times negative 2 is negative 6 plus 1. Going to be minus 5b. So b is equal to, what's 120 over 5? That's 12. So b is equal to 24. Pardon me. That would have been a blunder. Alright. So what do for a? Alright, so we have 3s plus 1. I want this guy to be equal to 0. So this is going to be, taking the 0 side, this is going to be minus 1. And then divided by 3, negative 3. Okay, so that's how you work around getting what set your coefficient to in order to cause havoc and find your numerators for a partial fraction. So 60 times negative 1 over 3 is going to equal a 2 minus 1 over 3. Okay? Where can I do this? Minus 1 over 3, that's minus 20. Is going to equal, what's that going to equal? 5 over 3a. Okay? 5 over 3a. So a is going to equal 3 times 60. 60 over 5 is 12. So a is going to equal to negative 12. Let's go off screen. Alright, so what do we have? We had 60s. S plus 1, s plus 2 was equal to a over 3s plus 1 plus b over s plus 2. So we found our coefficient and a was negative 12. I was minus 12 over 3s plus 1 plus, and b was 24. 24 over s plus 2. Aha. we can almost get on with the inverse Laplace now. 24 over s plus 2. We're practically almost due. What we need to do here is take note of this. Here we have s plus 2, and we're going to try to isolate only s here. The only way to do that is to factor out 1 over 3 from this denominator. Okay, so dividing this denominator by 1 over 3. 3s over 1 divided by over 3, not by 1 over 3. So 3s over 3 is going to be 1, and 1 over 3 is going to be 1 over 3. So we're going to bring out this 3. Okay, since we're dividing out 3, so v naught of s is going to equal minus 12 over 3. What is this? S plus 1 over 3, which is plus 24 over s plus 2. Over s plus 2. Amazing, right? Let's get to the inverse is equal to v naught of s. So, the really cool part, v naught of t is the inverse Laplace transform of v naught. I can't draw the left curly bracket. Okay, so that's the inverse Laplace transform of minus 4 s plus 1 over 3 plus 24 over s plus 2, which is very elegantly minus 4 e to the minus 1 over 3 t plus 24 e to the negative 2t volts. Amazing, elegant. If you do have any questions, please leave them down in the comments. I'll be more than happy, or you could post it in the community on YouTube. Yeah, I'm more than happy to take them. We've got one more. So solving this for t less than 0, the first thing we have to do is find our initial conditions. So at t less than 0, we're left with 12 volts and only our capacitor. Okay, which tells us that the v naught across our capacitor as vc naught is equal to 12 volts. This is very crucial. All the questions we solved previously didn't have initial conditions. This one is going to have. So our initial voltage across the capacitor is 12 volts. Okay, then we now go to t greater than 0, and then transform our circuit to the Laplace equivalent. Okay, so we have our capacitor. Since there's an initial condition, it's going to be this capacitor and the voltage source in series. Okay, and then all that's left is our resistor. The voltage across the resistor is going to be the same as the voltage across the capacitor and the source. Okay, the question is actually asking, this is a mistake in the drawing. The question is actually asking us to find the voltage across the resistor. Okay, so that's plus minus v. What is this going to be? 1 over sc. You call the frequency domain equivalent. So this t greater than 0. Frequency domain name. Okay, frequency domain. So for capacitors, it's going to be 1 over sc. That's going to be 4 over s. Okay, so this capacitance is going to have an impedance of 4 over s. Our source now is v naught all over s. So when you go for initial voltage, that's 12 all over s. And we can do the usual casual Kirchhoff's voltage law. So going this way, this has a value of 5. That's going to be 5 V's. This is 5. Alright, so 5i. Let's start with 4s. So 4s plus 5, all factors of I, is going to equal 12 over s. Okay? Is that it? Am I 4 over s? Golly. I just finished something else switching. So 4 over s plus 5 is going to equal 12 over 5. Let's try and see if we can add this fraction together. So that's going to be all over s, 5s plus 4, I is equal to 12 over s. So now we can see s goes away cleanly. 5 plus 4i is equal to 12. So I as a function of s is going to be 12 over 5s plus 4. Recall, we're looking for voltage over this. That's going to be current times impedance. All right, so V naught of S is going to be 5. Oh, not even I naught, since it's not initial. 5I of S. Okay, so V naught of S is going to be 5 times this. 5 times 12, is that 16? Yes, I believe 60. So 60 over 5s plus 4. Cool. Recall what we did in the last question. We need to get s alone here. So we're going to factor out 5 from the denominator. So V naught of s is going to be 60 divided by 5 is going to come out. So it's going to be s plus 4 over 4 or 5. I can go in 60. I believe this should be 12. So we now have our final expression for V naught of s. It's going to be 12 over s plus 4 over 5. Alright, we can take the inverse Laplace. So V naught is a function of time. We know this is the inverse Laplace of V naught as a function of s. Oh, that's a very bad bracket. Which is equal to the inverse Laplace of 12 over s plus 4 over 5. Okay, so that's going to give us 12 e to the minus 4 over 5 t volts. So solving with initial conditions isn't difficult at all. You just have to remember I think we'll cover that in a video. Remember your identities for capacitors and inductors with initial conditions. It comes from differentiating the derivative condition, okay? Because for capacitors, you have current is C dv dt. For inductors, you have voltage is L dt. So when you differentiate the derivatives and multiply them by capacitance, by inductance, you end up with a condition that tells you what happens when you want to deal with inductors and capacitors with initial conditions. So this gives us a source whose value is V naught all over S, and the polarity matters too, because this is positive feeding into the capacitor. For inductors, is reversed. Okay, so we'll do a video on that. I need to be careful. And the final answer was 12 e to the minus 4 over 5. This is 5. Trying to 4 over 5t.